Hi guys, Dr. Burns here. We're going to take a look at 9.2, which gets into the central limit theorem, this time for sample means. So we previously talked about the central limit theorem with proportions. Now we're going to get into what it looks like for means. So our sampling distribution for x bar is going to follow a normal distribution so long as certain conditions are met, similar to what we had previously in the course. So the sampling distribution for x bar is, I'm going to say approximately normal, where mu is still the population mean, sigma is the population standard deviation, and n is the sample size that we're selecting. What are the conditions that have to be met for the central limit theorem to apply? So here's the conditions. First, it has to be a random and independent sample, just like always. Each observation has to be collected randomly. And of course, they have to be independent of each other. The sample has to be large. So it has to be large enough this time. How large? It's a little bit different. The sample has to be at least greater than or equal to 25. And actually, one of two things can be true here. Either the population distribution is approximately normal, or the sample size is at least 25. So it can be the case that you've got a normal population and your samples are very small. Maybe you're only collecting 4 or 5 at a time. That's okay if the population is normal. Now, if the population is skewed or we don't know if it's normal, then that doesn't work. But if we're told the population is normal, the sample size does not matter. If we don't know that the population is normal, or we know that it's not normal, as long as we're above 25, then we're in good shape here. And then finally, the population has to be large. So the large population, if the sample is collected without replacement, the population must be 10 times larger than the sample size, just like it was in previous chapters. So as long as these conditions are met, then we know that our distribution for sample means is going to be approximately normal. And I'm going to write that up here. X bar is going to be distributed in a distribution that's approximately normal with a mean of mu and a standard deviation of our standard error. And that standard error formula is, just like it was previously, sigma divided by square root of n. And down here it says, note that the larger the sample size, the more precise the approximation. Remember what that means. Larger sample sizes mean smaller standard error. If the population is normal to begin with, as I mentioned previously, the sample size does not matter. Let's look at a quick example here. The mean length of time in hours that it takes a lacrosse team to play a game is normally distributed with a mean of 2 hours and a standard deviation of 0.5. A sample of 50, size 50, is randomly drawn from the population of games played by the team. Does the theorem apply? Well, they said it was a normal distribution, so that part of it is taken care of. But even if they didn't tell us that, what do we know? Well, was it a random sample? They said it was, so we'll assume yes, random and independent. Is it a large sample? It's large enough because n is 50 and it has to be at least 25. So n is greater than or equal to 25. The only condition that might be a little bit suspect is the population. Is the population at least 10 times the sample size? Well, I guess it maybe depends on what we just define as the population. All lacrosse games played by a team, 10 times the sample size would be 10 times 50, which would be 500. They are certainly not playing 500 games in one season. I think they'd be exhausted if they did that. We'll assume over all of the years that they're playing lacrosse, they've played more than 500 games. This is not a new team. They've been around forever. So we'll assume, yes, all games played are more than 500 games. So we'll say that condition is met. So then what does the central limit theorem tells us? It tells us that our sampling distribution for the mean length for all of their lacrosse games is going to follow a normal distribution. The mean is going to be what? The mean is going to be the same as the population mean, which was 2 hours. So mu is 2. The standard error is going to be sigma, which was 0.5, divided by the square root of n, which was 50. So let's put that into the calculator. And I am getting 0.071 if you round it for the standard error. So the shape is going to be approximately normal. Now let's take a quick look at what this would look like in the Art of Stats website. Let's do a quick simulation here. So I'm going to pull up the website and I'm going to put in the information for this lacrosse team. They told us that the population was approximately normal, all of their games. The lengths are approximately normal, so let me put that in. We're going to assume it's bell-shaped. Population mean, I believe, was 2 hours. And let me see if it'll let me put in, yeah, it will. So 2 hours for the mean. And the population standard deviation was 0.5. And my sample size was 50. So here's what the population distribution for all of their games looks like. So I'm going to start drawing samples, and I'm just going to draw them 100 at a time. And what I want you to observe is that the bottom is my distribution. So what's in blue is the sampling distribution. Do you see that it is approximately normal? It's got a mean of 2, actually. That's exactly the same as the population mean, and that may shuffle just a little bit here. But the standard deviation is 0.07. And hey, that's very close to what I said it should be. I said it should be 0.071. And there it is. It's pretty close. So let me go back real quick and just show you that one more time. You can see that the standard deviation, remember, is the standard error. There it is, 0.0711, 0.074. So it's shuffling around just a little bit, but it's very close to 0.071, as we said it should be. And I want you to see that this distribution is very close to a normal, almost exactly a normal distribution. And so guess what? We're going to use that later on to estimate different probabilities of getting different sample means using the empirical rule. So we'll practice it a little bit tomorrow in class, and I'll see you then.